Before we can prove the next statement, we need to introduce a new function. The Mobius function is probably defined very differently from most functions you've encountered so far in your mathematical careers, but it turns out to be both extremely powerful and incredibly useful in number theory. We will begin by looking at the definition. Definition: the Mobius function mu of n is defined as follows. Mu of 1 is equal to 1, mu of n is equal to 0 if p squared divides n for some prime p, and mu of n is negative 1 to the r if n is the product of r distinct primes. In other words, mu of n takes on various values depending on its prime factorization. If the prime factorization has a repeated prime, the value is 0. Another way of saying this is that if a square greater than 1 divides n, then mu of n is equal to 0. Otherwise, it counts up the number of primes in the prime factorization and takes the value plus or minus 1 depending on whether the number of primes is even or odd. We will now work through some of the main ideas of the proof of Theorem 6.2. Theorem: phi of n is equal to the sum of mu of d times n over d, where d divides n, and is also equal to n times the product of 1 minus 1 over p for all p dividing n. The large pi notation is similar to the sigma notation for sums, except that instead of a sum, it's a product. The proof proceeds by induction on the number of distinct prime factors of n. Suppose that n has just one prime factor so that n is equal to p to the m. In the previous video, we showed how to use a counting technique to show that phi of p to the m is equal to p to the m minus p to the m minus 1. Now that we have this formula, we're going to evaluate the sum. Notice that when we write out the sum, the only terms that we get are powers of p that are less than or equal to m. However, many of these terms evaluate to 0 because mu is being evaluated on a number that is divisible by a square. After evaluating the Mobius function, we see that the remaining terms match the formula for phi of p to the m. The second equality follows from this by just factoring out p to the m and noting that there's only one prime in the product. These two statements together completes the proof of the base case. The induction step is hard to conceptualize in the abstract, so we will work through a specific example. The idea is that we want to see what happens when the value of n has one new prime factor, so we will write n equals n prime times p to the m, where n prime has k distinct prime factors and p is a prime that does not divide n prime. Specifically, we will try to compute phi of 90 by writing 90 is equal to 10 times 3 squared, so that n prime is equal to 10 and p is equal to 3. Just as before, we're going to write the numbers from 1 to 90 and put it into a grid. Except instead of making rows of length p, we're going to make rows of length n prime, which is 10. This means that we will have p to the m rows, which is 9 in this example. Notice that all the columns contain values that are congruent to each other modulo 10, so that if one of them is relatively prime to 10, all of them are. The inductive hypothesis tells us that we know how many of these numbers in the first row are relatively prime to 10. In this case, it turns out to be phi of 10, which is 4, and the specific values are 1, 3, 7, and 9. But then the observations we just made about the columns being congruent to each other shows us that we must have 4 times 9 numbers listed here that are relatively prime to 10. We have not yet taken into account the numbers that are not relatively prime to the new prime. In order to count these, we will break up the rows into groups of p. In this case, we see that we have 3 groups of 3 rows. Let's focus on the top group. Which of the shaded numbers are multiples of 3? We have 3, 9, 21, and 27. Notice that this is just 3 multiplied by the original 4 numbers that we started with. Furthermore, each block will have the same pattern of removed terms modulo 30. There are 3 of these blocks, and each block has 4 extra multiples of 3 in them, so we must have that phi of 90 is equal to 4 times 9 minus 4 times 3. In general terms, we could write it like this. This represents the total number of terms that are relatively prime to n prime, minus the number of those terms that are not relatively prime to p. Using the inductive hypothesis, we can rearrange this expression to get the right product. In the last line, we simply rolled the 1 minus 1 over p term into the product by changing the index. The proof of the sum formula is somewhat intricate, so we'll have to discuss that later in class. All the details are in the book if you want to read through it. It's just a series of algebraic manipulations, but the justification at each line requires a bit of careful thought.
Thank you for watching this video. I'm currently dabbling with the idea of creating more videos like these for my classes, and I welcome constructive comments that might help me make better videos in the future.